as a reminder, when we're dealing with isomorphic graphs, in order to, or I really should say, if we're checking if two graphs are isomorphic, well, there's two ways to go about it. One is acting under the assumption that you think they may be isomorphic, and in that case, you're looking to build this function that is the isomorphism. The other one is looking to try to break it. In other words, see where these graphs really diverge or really are different from each other. Both strategies, totally correct way about going about checking to see if two graphs are isomorphic or not, but they are a little bit different in terms of your thinking process. Okay? Now, remember our strategy. So this one here, I'm not going to say it's the perfect thing in the world, but it gives you a game plan on how to attack the question of, are these two or more graphs isomorphic or not? First things to check are, do they have the same number of vertices and edges? That's your low-hanging fruit. Definitely always check that first. If you actually have graphs that have a different number of vertices and or edges, immediately they're not going to be isomorphic. You're done. Best case scenario. Okay? Second thing to check is the degree of all the vertices in all the graphs that you're looking at. Typically, we look at pairs of graphs, so you get a chart of the degrees. If you have the same number of each type of degrees in the two graphs, all that tells you is there's a likelihood that the two graphs are isomorphic. However, you still have to check that actually works. Now, we had two different situations. We actually had several situations, but we had two sort of quintessential situations or examples last time. One was where the two graphs had all the same degrees across for their vertices, and the other graph was where there was quite a few different degrees. If you actually have, or one graph has like, I don't know, every vertex has a different degree, and the other graph, every vertex also has a different degree, stop right there, see if that isomorphism works. And when I say that isomorphism, that would mean you'd match the vertices with the exact same degree, and it would be faster to check that one possible isomorphism rather than do anything else. But in reality, you normally have graphs where there's a whole collection of vertices that have the same degree. And in that case, it's almost more trouble than it's worth to try to find your isomorphism at this stage just off the degrees. Okay? But again, it depends on the variety among your degrees. Okay? Now, once you've got that all the degrees also match and you haven't gone the route of trying to build an isomorphism at that stage, the next things that you want to start looking at are the graph. Are you looking at subgraphs? And specifically here, this is where you'd want to do something like what we did yesterday, which is you build a subgraph based off of all the vertices of a certain degree. If those subgraphs are isomorphic, you get no new information. So you either do it again with another collection of vertices of a different degree, or maybe you move on to something else to check. If the two subgraphs are not isomorphic, so they legitimately look different, maybe they have a different number of edges. Okay? In that case, that tells you immediately that the original two graphs are not isomorphic, and you stop. I'd have a tendency to go to complements next, but you can also look at some sort of really quintessential either cycle, circuit, path. Typically don't look at trails, it's normally paths. But suppose you have noticed that one of your graphs is actually just one big long path. These guys are actually often called chain graphs or path graphs. They have a special notation which we'll get to later, which is P with a subscript N. P for there's just a single path. But if you notice that one graph is just one big old long path, then the other graph better be the same, so you try to untangle it and see, hey, could I rearrange these vertices and get one graph? One path, excuse me, it's already a graph. Complements, we did an example with complements before. The only time that complements are actually going to help you is if you get fewer edges in the complement than in the original graph. So these guys would be when your original graph has a ton of edges in it. And we gave, I believe, an inequality of how you can check to make sure that you have sufficiently many edges where this would matter. Okay. And then if your graph is a special type of graph, like we talked about bipartite graph, I think last time, that would also be something that you check between them. But this is the first thing typically people look at are subgraphs, and then you start checking the other things depending on what graph you actually have and how much work you want to put into this. Okay. So that's the background there. Now, in terms of what we did last time, we looked only at simple graphs. So we only looked at graphs that had undirected edges. There were no multi-edges whatsoever. Technically speaking, you can have directed graphs to be isomorphic. You can also have multi-graphs to be isomorphic. If you have multi-graphs to be isomorphic, if you have two vertices and there's, say, two edges between those two vertices, you have to make sure that same property happens in the second graph. Same deal with loops. If you have a loop in the first graph, you have to have a corresponding loop in the second graph. We're really not going to deal with multi-graphs and isomorphic, whether multi-graphs are isomorphic, but you totally can do it as well. But I did want to go ahead and give us an example dealing with digraphs or directed graphs. Okay? So some of the stuff that you would do is exactly the same as if this was in a simple graph, but there's one extra thing you have to worry about. And the one extra thing you have to worry about is not only do all of the vertices in the first graph have to be able to be mapped to all the vertices in the second graph, you still have to keep all of your corresponding edges, so that's the same as a simple graph. But now with the edges, not only do they have to correspond to the edges in the second graph have to correspond to the edges in the first graph, they also have to be going in the same direction. Okay? So that's the extra piece when you're dealing with your directed edges and you're checking to make sure it works between the two graphs. You have to make sure that the direction of the directed edge also translates over to the second graph. Okay? But that's sort of a last thing that you would do. First thing that you would do is the exact same first thing that you would do with a simple graph. You check the number of vertices and the number of edges. So first step. So what do you guys think? Number of vertices, and let me go ahead and label this like we didn't really do last time. In that first graph, how many vertices do we have? Yep. And because there's numbers in the second graph, we also have 8 vertices in the second graph. And here's now the big question. How many edges do you think are in these two graphs? Out of the easy graph, there's 12 in D2. All right. Now, this here, not going to lie, often people don't get 12 edges for this first directed graph. So what do you guys think? Are they correct in saying that there's 12 edges? Yeah. Now, what's the key thing? So here's the mistake that people will make. Notice how these edges right here, it looks like they intersect at the middle. Just because edges in graphs cross each other doesn't mean there's a vertex there, so watch out for the vertices that are actually labeled. And in the future, we're going to get graphs where the vertices aren't labeled. Watch out for these big circles. That's one of the reasons why, I don't know if you guys noticed or not, I went back and put in the circles for the vertices over here because I had forgotten to do that when I prepped up this graph earlier. So, yep, you've got the 1, 2, 3, 4, 5, 6, 7, 8 edges that look around in this sort of polygonal shape. And in the middle here, you've got 4 of them. This whole guy, D to H, is 1 edge. So, yep, we totally have 12 edges. Now, pluses and minuses for getting that answer of 12. Pluses, that means there's a possibility that these two directed graphs are actually isomorphic and just drawn in a slightly different orientation. Minuses, we actually now have to do more work. It all depends on what it is that you guys like to do. If you want to be super lazy, getting it where you don't have an isomorphic graph, at least in the easy sense, is typically something that you look at. All right, so next thing that we do is we look at our degrees. Now, here's the fun part. When you're looking at degrees, I think I can actually put this sideways. I've got just barely the right number of space here. We are now in a directed graph. Anybody remember what's different in a directed graph with respect to degrees than when we were dealing with our simple graphs? So your degree isn't just the degree of the vertex. You have both an in degree and an out degree. So if we look at these vertices in that first graph, D1, what do you guys think the in degrees are? Well, let's start off with A. What do you think the in degree is for A? Yep. Now, what about for B, C, and D? What would be the in degrees for those guys? Yeah, they're actually also all going to have an in degree as 1 as well. But what about for the last 4 vertices? Are they going to have an in degree of 1 or something else? You're already answering. Awesome. Yep, the last 4 have an in degree of 2. Now let's check for our out degrees. What do you think the out degree is for, and let's just group them together for the first 4 vertices, vertices A through D. Any guesses on the out degree for those guys? Yep. So here for A has an out degree of 2 because you're going 2B and 2E. And the same thing happens on each of these next ones. You've got one of the out degrees corresponds to the edge that's going around the polynomial. The other out degree corresponds to that guy that looks like a diagonal. It is. So we'll have 2 for all the out degrees for the first 4. And the last 4 vertices, we're going to get an out degree of 1 because when we're over here, say we pick on F because that's where my cursor's, my little arrow, well, it's not an arrow, my little guy here stopped. The diagonal is coming in. We got one of the sides that look sort of on the polynomial edge coming in, but only one going out. Yeah. Now, if we try to do the exact same thing for our second graph, a graph that kind of looks like a box, let's see if we actually get the same results. So the only way that this second graph could possibly be isomorphic to the first graph is if we have the same number of in degrees that are in degrees and out degrees of 1s and 2s. In other words, we need 4 in degrees to be 1 and 4 in degrees to be 2. And apparently I cannot write and talk at the same time today. So what do you guys think? What would be the in degree for vertex 1? Yep. Now, what do you think the in degree is for? And let's just do the entire top of that graph for vertices 1 through 4. We already found for vertex 1, but what about for 3, 4, 2, 3, and 4? Yeah, they look like they're all actually have an in degree of 1 up there at the top. Now, if we then look at the bottom of the graph, so vertices 5, 6, 7, and 8, if we want to have a hope of these 2 digraphs being isomorphic to each other, the rest of the in degrees really need to be a 2. Do you think that's true when you look at that second digraph? Yeah, so it does turn out that all of these guys are 2. Now, notice the orientation or the order of those in degrees and out, those in degrees being either 1 or 2, actually total coincidence, but turned out to be the exact same pattern that we had in the first digraph, which means in order for the out degrees to also line up, we should be getting 4 2s and then 4 1s in that same order. Let's check to see if that happens. If we look back at the vertices 1 through 4 at the top of the graph up here, does it look like all of them have an out degree of 2? Yep, so I'm just going to pick on this one here, 3, because I'm right next to it. 1 edge is coming in from 4, 2 edges are coming out, going to 2 and to 7. And this is true because up here at the top, we've got a nice little circuit going on inside of a directed graph, so notice the arrows. And what that means is, based off of just these 4 edges, you get 1 edge coming in and 1 edge coming out, but also all 4 of these edges, all 4 of these vertices have an edge dropping to the bottom half of the digraph, and the directions on all those edges are going down to the bottom half. That will give you the 2 that we were looking for. Now, using that same logic, What do you think about the out degree for vertices 5 through 8? We are hoping it's 1. I see 1 vote for 1. What do you guys think? Are all of these last blanks, should I fill in a 1? Is that correct based off of our graph? Got 2 votes for doing it. It turns out, yep, that totally works. And that's because I'm going to pick on 7 right here. We've got 1 edge coming in from the top, and then we have another little circuit going around the bottom right here, which means we have a second edge coming in, but only 1 edge leaving to travel around that sort of circular pathway at the bottom there. Okay. Now, good news, bad news. Good news is this definitely indicates that there's a possibility that those 2 graphs are in fact isomorphic, and there's not actually enough information to tell you for sure that they are isomorphic. At this stage in the game, or at this stage in working the problem, you then know a couple of extra pieces of information that you didn't know though earlier. And those extra pieces of information are, if you have an isomorphism, vertices A through D are going to have to be mapped to vertices 1 through 4. Unfortunately, that still, if you have no idea how to map them together, gives you 48 possible different isomorphisms that could actually be in play here. Let us not actually write them all down, because that's just too much work. So instead, this is when you start thinking about, hey, maybe I need to check some property. Now, we actually tagged on a property when we were looking at this second, or noticed a property when we looked at this second graph. And that property was the fact that the top of the graph has this little circuit, and the bottom of the graph has the little circuit too. So it might be something to look at to see if there are any distinguishable or memorable in some way circuits between the graphs. So if we look at this first guy right here, typically what you do is you try to find the largest circuit possible. Anybody have a guess on the largest circuit possible that we could find in that D1 graph? Yeah. So it's actually one of the things we kind of sort of behind the scenes noticed earlier as well was the fact that you could literally just go around the outside. It looks like a polygon, and if you notice, the directions here are going to matter for the directed graph. All these directions are pointing in the same way. So you could literally do exactly what one of you put in there and said, hey, start at A, B, C, D, E, F, G, H, and then go back to A at the end. Okay? So this means you could totally pick up a circuit that deals with all of the vertices. That is a memorable circuit. Okay? In other words, it's going to be a unique circuit, something that is not just some random circuit that you can find in any old graph. So let's see what that length is. How many vertices, how many edges did we use? 1, 2, 3, 4, 5, 6, 7, 8. And we said A, B, C. Just go along the complete outer edge there. And don't forget to get back to A. Okay? So now we go to the other digraph. And the only way that these 2 guys would be isomorphic is we'd have to find a circuit in the second graph that also has length A, and 8, excuse me, 8. In other words, since there's 8 vertices, we need to find a circuit here that goes through all of the vertices. So what do you guys think? We already talked about that we had 2 circuits of length 4, so they included the top and they included the bottom. Do you think we could get a circuit of length A that picks up all the vertices? So you guys look at that for a second. Ooh, I have a guess. All right, so let me get to a different color so we can keep track of the edges as we go. Oh, I'll go with the highlighter. So suppose we start at 3 and then go around to 4. That works just fine so far. Now then at 4, we want to get to the other vertices, so that's fine. So we're going to drop down here to 8. Then we'll have to go ahead, That's the only problem with this highlighter, is it's directional. Then we'll follow here the edges, the directed edges, and we'll get to 7. And remember, we were trying to get to a circuit, right? Which means we want to try to get back up here to the top. And what's the problem? You can't get back up. So that's exactly what a couple of you guys have been commenting is you can totally make a path that collects all of the vertices relatively easily. The problem is because of these 4 edges that are going from the top of the graph to the bottom of the graph are all pointing in the exact same direction. Once you reach all of the vertices in the top half of the graph, you jump down to the bottom half of the graph. Once you're in the bottom half of the graph, you're never going to be able to get back up. Yeah, so the best we can do here is exactly what the last comment came in is the best you're able to do is a path, but not the circuit. Let's check. 1, 4, 8, 5, 6. Yeah, you can't go back up on that edge 7 to 3. So that would be the issue right there is anytime you have one of these higher numbers of the 5 through 8, all of these edges that look vertical in the drawing are going to, they're going the wrong direction, basically. If even one of them had been pointing upwards, we could have started at a different place, top or bottom, and been able to make it work. So, conclusion. And let me make sure that this is actually not a highlighter because I think it still was. Conclusion, when you are in D2, I guess I didn't need actually the colon. In D2, there is no circuit of length 8, but we did find 2 of length 4. Unfortunately, that's not sufficient to make it work. Okay. Now, overarching conclusion. What do you guys think? Are those 2 directed graphs going to be isomorphic or not? And that would be the correct conclusion that a number of you are now sending in. Yep, these 2 graphs then are not isomorphic, and that is because there's something in one of the graphs that's not in the other graph. So our conclusion is directed graph number 1 is not isomorphic to directed graph number 2. Oh, that is a really good question. If it was not a directed graph, I actually didn't check that ahead of time, but we probably could check a little bit. Everybody has degree 3 if it's not a directed graph, so that's no worries. You could find one big overarching circuit here. And here you actually would be able to get the one big overarching circuit. So I would say yes, if it wasn't directed, this one looks like it would be isomorphic. So notice the direction on the edges really do affect whether the graph is going to be isomorphic or not. All right. So next question. Let me actually pull this so we can see where the question starts relatively easy. The next question asked us to do the following. List out all of the let's check that I didn't pre-write this one. No, I did not. All of the non-isomorphic simple graphs, and often people won't bother with the word simple here. They'll just say graph. If all you see is the buzzword graph, we typically assume that it means a simple graph, unless from context it's obvious it's a different type of graph. So this is our next question that we want to do. Ooh, just a second. Ooh, that is actually a good question. So the question is, when you guys are showing work, you need to follow all these steps or just write down what the general property is. Good question. It depends on the graph. So if it's going to be, so when I grade with couple of different things in mind. If you just want to get the result of whether something's isomorphic or not, if you write all of this stuff like on Scratchwork, but the only thing you actually say in what you send to me is this last bit right here that we titled Step 3 and 4, that would be sufficient. Okay? That would actually get you to the answer. But one of the things that I do in grading is I also check to make sure that you're thinking about the problem in a way that actually works. It doesn't always have to be the way that somebody else does it, but it has to be a way that logically works inside of whatever math you're doing at the time. So having these original steps here would definitely be something to think about. But if you can do this stuff right here in your head, I'm okay with it, unless the question is actually asking you to write everything out. And especially in something, so it would really depend a little bit on context. And the reason I say that is because I've definitely had people only do what you're asking about, which is only, like in this example, write out the paths here. But they did way more work than they had to because, like, there was a different number of edges in the two graphs. Okay, that would be my hesitation without just saying yes. All right. So for this particular question, it also has tied with it, before we actually write out all of the pictures, and we're going to actually write out all the pictures here in just a second. Let me share this with you. I have put together for us with a couple of the examples for today, some preliminary questions for you guys. So take a second, think about it. If you were asked to list out all of the non-isomorphic simple graphs where you only had two vertices, how many of them would you expect that you think you might have? Okay? So that question is currently active. Take a second for a guess. I put in a couple of different numbers there. And don't worry if you're not perfect. We're going to actually draw out the graphs here in just a second. But in these type of questions, which is a relatively common type of question, this how many non-isomorphic graphs are there, or what are the non-isomorphic graphs, having a little bit of an idea of how many you might have would be nice. It is specifically asking, so say there ended up with, I'm just picking the first number I saw from the list, say there ended up to be, the answer is 4. What that would mean is all 4 of those graphs are not isomorphic to any other graph in that collection. That would be what it's talking about. So it's what would be, so in terms of what you're asking, you're looking at pairwise non-isomorphic, meaning you could pick any pair in this set of graphs and they wouldn't be isomorphic. But it's not how many pairs of graphs aren't isomorphic. It's how many graphs that you can draw out that are different, that didn't turn out to be isomorphic to one of the other graphs. It's a way in math that we say, all right, I don't want to duplicate pictures. How many legitimately different graphs are there on two vertices is another way to think about it. And I would definitely recommend, if you have a chance to like sketch out these things, do it. And we're gonna do it here in just a second. I'm gonna wait till there's a few more people with answers before I draw the pictures though. All right, it looks like the number of people answering has stabilized a little bit. So let's go back and actually look to see what happened. So if you're looking at graphs on two vertices, the first thing that I always do is I always just go ahead, I don't remember what color I am, make sure that we're black. I always just go ahead and draw out two vertices, okay? So here's a graph, and what do we know about graphs? We know that we can put everywhere from 0 edges on it all the way up to k, and the subscript is whatever the number of vertices are. So this guy right here would be it would be the graph with the fewest edges, because you can't get less than 0 edges. So I'm just going to go ahead and call this graph G because I was super duper lazy. Now, one of the things that sometimes people do is they'll also then look at the other extreme, and they'll look at K2, and this would be all the possible edges that you can put on two vertices. Anybody remember what K2 looks like? Yep. So it's just a single edge between the two. So you're legitimately here looking at like the smallest graph, and then we just built the largest graph with respect to number of edges. Now, here's the big question. Do you think there's another graph? Is there anything that's different than either just only the vertices or just the one edges? Ooh, I like how you think. So right now we are on simple graphs. So with a simple graph, this is all you got. Okay? Now, what happens if it was a directed graph or a multi-graph? With multi-graphs, you can always keep on adding extra edges or extra loops. There's not a maximum in terms of number of edges with multi-graphs. I've definitely run into that horrible thing in the past. However, with directed graphs, you can do this same exact thing. So let me go ahead and write out the same question, but now with directed graphs. So here, I'm going to shorthand it. So this one is, again, we want directed graphs, so digraphs on two vertices. And again, we want them to be all non-isomorphic. Almost missed that middle syllable. All right. So when you switch from simple graphs that have the undirected edges to the directed edges, you have some extra options, but the strategy is exactly the same. And yeah, it looks like you guys answered your own question. Awesome. So here, I would again recommend going ahead and drawing out or marking the vertices first. So could you have the potential where you only have the two vertices? Yep, you totally could. That's exactly the same as a simple graph. This time, I'm going to go ahead and box this guy just so it's easy to tell who's the graph and who isn't, because that's a disconnected graph right there. Now, what's something else that you could have that is a graph that's legitimately different than the one that we currently have? Yeah, you could put in one edge. And with a directed graph, there's two ways to do that. So we have A, we have B. We also have A and B, but the arrow going in the other direction. And I'll go ahead and box this one up here. I should not have connected those boxes. That looks funky now. Oh well. Now, before we box the one below, oh, yes, let me go ahead and grab the one that somebody sent in. You also have the situation where you have two edges, A to B and B to A. And remember, in a directed graph, you do have to go ahead and draw it as two separate edges. Okay? Now, at this point in time, what do you guys think? Are there any other possible ways that we could insert edges on two vertices? I know the thing I always want to do is put a loop on here, but with regular old directed graphs, you're not allowed to put loops. Correct. The only time you're going to get multiple edges in a directed graph is when it's called a directed multigraph, and it would have actually set it up here. It would have to have the two words directed multigraph. So if you're only doing the digraph, you're not allowed to have loops and you're not allowed to have multiple edges. The only quote-unquote multiple edge that's sort of allowed is that guy, but it's not considered a multiple edge because they're going in two different directions. Even though it looks like there's two edges there, and there are two edges, they're not considered the same edge, which is the multi-edge. The multiple copies of the same edge is the multi-edge. So with that aside, what do you guys think? Is there any possible way to put in another edge onto two vertices than what we've already listed? And you guys are correct. So these are the only four things that we could legitimately draw in terms of edges on two vertices. Now, that takes care of drawing all of the graphs. except there's one last thing you have to check. And this wasn't an issue back on the other case because we just had the situation of no edge or one edge. Up here, the two edges, well, there's no other way to draw it. The no edges, there's no other way to draw it. But these two guys here, yes, they are actually isomorphic to each other. We could cross off this label here at A and replace it with a B. We could cross off that label B and replace it with an A, and then it would be the exact same graph. I'm going to draw the isomorphic symbol sideways. Wow, apparently I can't draw it sideways. Just a second, we're going to try again. Okay. Those two guys are actually isomorphic, which means that one below the boxed pictures is not actually, would not actually be one of your answers. You'd either choose that one I crossed off or the one that we had boxed earlier. So if somebody had asked you, all right, how many non-isomorphic digraphs are there with two vertices? The answer would be 3, but you have the option to pick which of those two orientations you want to write out. Although, quite honestly, people normally don't label the vertices anyway when they're listing out these guys. Okay. Kind of makes sense, a little bit makes sense so far. I'm crossing my fingers, although you can't see it. I'm going to assume yes, and I see one yes came in, awesome. So I have one last example of these type of things, and it's if we have more vertices than just 2. So suppose we wanted to do the same thing, and I'm not going to do it with digraphs. I'm going to go back to simple graphs. So the only thing I'm going to change in this next example is I'm going to change the number here 2. I'm going to change it to 4 vertices. And I want to do that because if you have more than 2 vertices, you actually have a couple of other strategies that you wanted to watch out for. So to grab the question is, do we need to worry about labels if you're talking about the isomorphism? So if you're going to talk about the function, yes, you have to have labels on the 2 graphs. Most people will, well, I shouldn't say most people. I normally, for the 2 graphs, do something like letters on one and numbers on the other just because it's really easy for people to then tell which vertex came from which graph. But what is really, really, really common is that you have letters on one graph, same letters on the second graph, but there's primes. Okay. We haven't, so it would be like this. And that's a way to show your reader or yourself how the isomorphism works. And this shorthand actually is a way so that you're not writing out the isomorphism in a chart while you're still figuring it out. Okay. So if that's something you guys want to do, you can. But if you're just writing out the non-isomorphic graphs, people often will not label them until they start trying to figure out, all right, are these 2 graphs isomorphic to each other? Then they start putting on labels. But that's only because you're dealing with, behind the scenes, the isomorphism. And that function requires some sort of label to be able to talk about it. So, question, we're going to list out the non-isomorphic simple. So we're going back to simple graphs. And I put simple in parentheses just like before because, again, that is typically not a word that's used. Okay? Typically, they're just called graphs. Now, in this case, I'm going to go ahead and organize these. So I'm going to be strategic about this. And the way that I'm going to be strategic about this is actually the same thing we did on the last 2 examples. Notice how, and we didn't focus on it while we were doing it, but notice how these guys are structured by way of their edge count. So the graph with the fewest edges came first, and we built up to all the possible edges. I'm going to do the exact same thing here. Okay. So if you have no edges, so zero edges, any guesses what the graph would look like? Don't overthink it. Bam, that's it. Okay. Now, if you have 1 edge, how many graphs do you think we're going to get that are not isomorphic to each other? That's the key. Yep, just 1. Why? Because if you went and drew the second one, maybe put the edge on the outside instead of the diagonal. Notice, while you could physically put the edge anywhere you wanted to, along the outside edges or either of the diagonals. So there's 6 possible edges you could grab. As soon as you're saying don't list somebody who's isomorphic to somebody else, these 2 graphs are isomorphic to each other. In terms of the isomorphism, the endpoints of the edge will map to the endpoints of the edge, and the 2 lone vertices would map to the 2 lone vertices. So it ends up that you're only going to get one of these guys. So you're not going to have any of those extra copies. Okay? Why? Because all those extra copies are isomorphic to whichever reference graph you originally got. Now, as soon as you start dealing with 2 edges, then you're going to get a couple of different types of graphs that work. So I'll do one of them. There's a lazy person's one. Yep. So you've got 2 lines. These 2 lines could also be the 2 ones that would look horizontal. This guy would also be isomorphic to if you pulled your 2 diagonal edges, because if you pull the ones that crisscross here, they don't actually meet at a vertex, so they would still be 2 disconnected, essentially, edges. Okay? And then the other one is if you actually have where the 2 edges share an endpoint or are incident to each other. And this guy here, you can pick specifically a bunch of different edges. It could be rotated, so where the 2 edge, so where you could have this vertical line and the bottom edge, the other vertical line and bottom edge, the same top but the other side. You could also pick one of the diagonal guys and one of the outer edges. So the key thing here is notice 2 edges that don't touch, 2 edges that share an endpoint, or if you will, all degree 1 vertices, 2 degree 1 vertices, 1 degree 2 vertex, and 1 degree 0 vertex, is if you're thinking in terms of degrees. So these would be the only 2 guys that are not isomorphic to each other. Every other graph on 4 vertices, 2 edges would be isomorphic to one of these 2 guys. Watching out for the degree has a tendency to be really helpful. Or the relationship between the edges can also be super helpful. Okay. Now with 3 edges, there's more things you can do. So any guesses on what you can do with 3 edges? There's at least 2 different things you can do. All degree 1. You actually can't get all degree 1, but you can get almost all degree 1. Yeah, it looks like you guys have got all of them. So you can have a single path. This is actually something you can always have. Well, you can always have it when you have the same number of edges. That's 1 less than your number of vertices. So here, I went ahead and just did a single path where I connected everybody together. You've got 2 degree 1, 2 degree 2. I think the first one was all degree 1, so the closest I can get to all degree 1 is something that's actually called a star graph. Doesn't look like a star in this orientation, but all of the edges are incident to one of the vertices. Ooh, I like the way you did that picture. That was very ingenious there. And then the last one is this guy. And I believe this is what one of you was trying to say. Yes, exactly the description that the last one came in. And the last one here is what looks like a triangle. And the thing that everybody wants to do is you want to put in like an edge to make it look like an arrow, but you can't because as soon as you put in that extra edge, it'll be 4 edges. So we'll have that next time. Notice something that you can do. You can actually just sort of think of all the different ways that you could put in edges. But notice also, stop doing that finger. Notice also from these previous 2 pictures, if you add an edge at the bottom, you get this one. If you'd add an edge at the top, you get somebody still isomorphic to this. If you add one of the diagonal edges in, you also actually get somebody isomorphic to this one. Yep, it is. And this one over here, if you add one of the bottom or side edges in, you would get somebody isomorphic to this one. Here, if you added this middle diagonal in, you would get that one. And if you add the other diagonal in, you would get this one over here. So that was one of the big things that I wanted to give you guys a clue in about when you're dealing with things that had more than like 2 or 3 vertices, you start thinking of these patterns of take everything I had previously and now just how do I add in one extra edge and where can I add it in? Now let's go ahead and finish this guy out. If you have 4 edges, anybody have a guess on what these graphs could look like? Oh yeah, that's definitely the one that I wanted to draw first. So you can totally do the standard guide to make something to look like a box or a square, and that totally works with 4 edges. You could also get it from one of the previous graphs by just putting in the edge here at the top. You can. I'm not going to though because I want to show something else at the end. Now, there is another way that you could have 4 edges here on our 4 vertices. Yes. And this depends on whether you want crossing edges or edges that don't cross. So, if you look at the middle graph from above, you could just do something like that by adding an extra edge. But maybe you were thinking of that triangular graph and really thinking in terms of arrows previously. So maybe you drew somebody like this, but the thing is, those 2 guys are actually isomorphic to each other. So make sure you only pick one of them. Which means if we actually write some scratch work over here to the side, which we'll do later, we'll do the count. And down here at 4 edges, it turns out that there's actually only 2 non-isomorphic graphs. The key buzzword there is non-isomorphic, because if you're looking at every graph, there's a lot more, but there's multiple copies of the same thing, and that's why we talk about non-isomorphic graphs. Now, 5 edges. Any guesses what this graph would look, what a graph on 4 vertices and 5 edges might look like? Or maybe I should rephrase. How many of them do you think ooh, there we go. 2 triangles. I was trying to think how you guys would communicate that to me. But yes, 2 triangles definitely works really well. And it could either be 2 triangles where there's no crossing edges, but you could also think of it if you pulled from this picture above, it would look like this. Where it looks like there's 2 triangles sort of overlapping each other. But both of those 2 guys are isomorphic to each other. One of the ways to see that is if you take this vertex here I'm trying to highlight and you moved it to below, sort of unfolded the triangles, and then you got the same picture over here. So it turns out that there's only one graph that has 5 edges and 4 vertices, or I really should say all graphs on 5 edges and 4 vertices are isomorphic to this guy. Now, last thing, and why would I say 6 edges is going to be the last picture that we can do? Because this is going to be our complete graph on 4 edges. This is the guy that looked like a box or a square with 2 lines crisscrossing, or if you want to be super duper fancy, you can draw it like this. And that's how to draw it with no crossing edges. But they are isomorphic to each other. Now, here's why I listed them out in the way that I did. First thing is, let me go and erase some of our scratch work. I want to erase that guy. And then let me get a different color, just so I can highlight. If we look at how many graphs are in each one of these rows. If you have 0 edges, there's only 1 graph. If you have 1 edge, there's 1 graph. If you have 2 edges, there are 2 non-isomorphic graphs. 3 edges, 3 non-isomorphic graphs. 4 edges, there was 2 non-isomorphic graphs. Don't double count. 5 edges, there was only 1 non-isomorphic graph. And on 6 edges, there was just a complete graph. Anybody notice a pattern with the number of graphs on each edge count? Yeah. So it does turn out 0 edges and 6 edges are totally going to have the same number. 1 edge, 1 less than all the possible edges you could have. It kind of does resemble the Pascal's triangle or the n choose something. It's not exactly the same because these aren't exactly that, but it has that same sort of vibe to it, that same, in math we call it symmetry. Here's the reason why. These guys down here at, I'm going to pick on 5 edges. If we have G up here at 1 edge, the guys down here at 5 edges, those are the complements. Yes. And that would be why you have the exact same number, because once you find it up here, when you take its complement, well, if there's only one guy that's not there's only one copy, everybody else is isomorphic to this guy, same thing is going to occur when you get to the complements. This is also a fast way to build this chart. You can build it from the top and the bottom at the same time. Grab the ones with no edges, grab the complete graph, then 1 edge, and then all of these complements will give you 1 less than the total possible edges you can have, and so forth. So that's another trick that you can do. You don't have to do that trick, but it's something that some people like to do. It's not really saving you work because you still have to find the complements, but it means as long as you're comfortable with getting the fewer edged situations correct, it's easier to deal with when you have more edges. Although quite honestly, the ones that are the hardest to find are the ones right in the middle right here. But just as a heads up, that is a strategy. Questions make sense? Hopefully a little bit comfortable with that. I made sure to do this because you got a homework question similar to this. And if you see it without having any sort of context, it can be overwhelming for sure. All right, I am not seeing any comments or questions come. Oh, there's one. I'm not sure if I'm misreading your question or if there's missing a word. So the ones in the middle, you're talking about these guys right here will always have an amount equal to. The ones in the middle here, not necessarily. Gotcha. All right, so awesome. That was what I was thinking when I just finished reading that out loud. So there's no guarantee that the number of non-isomorphic graphs is going to match the number of edges you have right here. Now, what is guaranteed is the case where you have the most non-isomorphic graphs is going to be when you have the total number of edges you possibly could have divided by 2. So here, 6 divided by 2, 3. This is where we're going to have the most number of non-isomorphic possibilities. If this had been, I don't know, 11 edges, you divide 11 into 2, and that's 5.5. So in that case, both when you have 5 edges and 6 edges, you would have that would be when there would be the most number of non-isomorphic graphs. But not really a guarantee that there's going to be 5 or 6 of them. In that case, actually I haven't done that one in ages. There would be the same number across the 2 of them. So in this case, it was more coincidence, 3 edges and 3 graphs. The thing to take away is really that this guy here was where you had the most non-isomorphic graphs. Because the more vertices you have, the more non-isomorphic graphs you're going to start coming up with. All right, so I've only got one last question prepped up for us in this section, and then we'll start looking at section 1.3, and based on time, we'll finish up section 1.3 on Tuesday. All right, so example, and this example is going to go back and look at 2 different graphs. They're actually both graphs that we've looked at before. And what we want to know is, are they isomorphic? So are G1 and G2 isomorphic? So here's the first one. It's going to look like a box with another box inside of it. So let's see here. I'm trying to match my labels. And I try to match my labels with my notes ahead of time. That way, if there is an isomorphism, we don't have to build it completely from scratch. Although half the time we do anyway, because you guys find another isomorphism than the one that I originally found. All right, so E and F, H and G. So this is the first one. We'll call this one G1. And then over here, this one is going to look like a wheel. Actually, I shouldn't say that. It actually is a wheel graph. But it's going to look like an octagon. with all of the diagonals on the inside. And this one I'll be lazy and just labels 1, 2, 3, 4, 5, 6, 7, and 8, and put in these middle guys. So this really looks like our example with the two directed graphs that we had at the beginning of today, except they're not directed. So similar-ish, but not exactly the same. Ooh, I probably should have matched them, and then the question that you guys had earlier about whether if we remove the directed edges, we could have matched exactly. Downfall there. So let us go ahead and check to see if these guys are isomorphic. First thing is we'll check vertices. I suspect you guys have already checked this. These guys have 8 vertices and 12 edges each. And since they're similar to what we did before, I'm not going to go over actually counting them up again. Okay. Now, in terms of the degrees, if we look at all these degrees, all of the degrees are what? Well, they're all degree 3. And what that tells you is, well, it tells you maybe complements might work because there is actually a fair number of edges here. But it definitely tells you that using that technique with subgraphs isn't going to work. Now, previously, when we, at the beginning of today, our first example had 2 graphs that were very similar to this, and we looked at circuits. And we said, hey, is there a way that we could find a complete circuit on both of these 2 guys? And in this particular case, this one, you could do a circuit like we did before, just all the way around the outside. This one, let's see, A, B, C, D, H, G, F, E back to A. So they actually both have 2 complete circuits, which implies maybe they actually really might be isomorphic to each other. So both of them have a circuit of length 8. So this one has circuit of length 8. Now, I'm not going to lie. If it's late at night, that definitely feels like these 2 guys should be isomorphic. But unfortunately, if you have the same property in both the 2 graphs, until you actually build the isomorphism, there's no guarantee that these 2 graphs are in fact isomorphic to each other. And this is actually an example where I wanted to show you one of the properties we talked about but haven't actually used yet with isomorphisms, and that's checking to see if your graph is a specific type of graph, specifically if it's a bipartite graph. Okay? So why would I even think of looking at bipartite graphs? It's because this one right here looks like we could actually group our vertices in 2 distinct groups. Anybody have a guess on which vertices look like they might be able to be grouped together? Yeah, that's totally my initial guess too. But before we actually put them in that order, I actually want to show you the way to guarantee that it's going to work for checking to see if you're bipartite or not. So this is, in fact, kind of showing you a test for bipartiteness as well as dealing with isomorphisms. Ooh, yeah, there's another guess. That is not the one that I came up with. So let me show you a strategy that works there, but there are more than one way to, there's more than one way to divide your vertices into 2 groups. But they are going to divide into 4 vertices and 4 vertices. The first thing that you do is you pick your favorite vertex. It looks like most of you picked, nope, can't say that. Many of you picked A. So I'm just going to be lazy and pick A. Okay? I'm going to need to throw down the menu up top. That way I can switch between colors when we do this. All right, so if you look at vertex A right here, notice A is connecting to who? According to the edges that A is an endpoint of, or that A is incident to, A is supposed to be adjacent to B, to E, and to D. Now, what does that tell you about B, E, and D? That tells you that B, E, and D have to actually be on the other column of our bipartite graph. So I'm just going to write them down. So here we've got B. I am now regretting putting this below. So B, E, and D. Now we know that A is is adjacent to all 3 of them. So I'm just going to copy down the edges from A to B, A to E, and A to D. In other words, we're going to redraw the graph into 2 columns is what we're trying to do. Now remember, bipartite, the edges are only allowed to go between the 2 columns, so the way that you would fail to be bipartite is if you have an edge inside of one of your columns. Now, once we've grabbed A, next you want to grab either B, E, or D. We'll do all of them, but let's start with B first. So if you're at B, B has degree 3, so that means it's adjacent to A. We've already got that edge in the new drawing of the graph. B is adjacent to F. Well, F then has to be in the other column, so we'll go ahead and draw in F, and I'll put in that edge. And B is also supposed to be adjacent to C, so that means C is in the other column of the graph, and I'll go ahead and put in that edge B to C. Okay. Now, once you've got dealt with B, B down here now has degree 3, you're now ready to look at either E, D, F, or C, and it doesn't matter which one you do. So maybe you pick, I don't know, maybe you pick E because it was right below B. So E here is adjacent to A and F. We've already got the edge E to A, but we can put it in the edge E to F. And E is also adjacent to who? E is adjacent to H. Okay? So H is not in the picture yet. So if we go ahead and put H in our picture, it would have to be in the column opposite of E, and we'll go ahead and put in that edge. Now E has degree 3 in the new drawing of the picture, so we're done with E. Next, maybe we go to F. F currently is degree 2 in the new picture. We know it's degree 3 in the original graph, so that means we're missing somebody. So F is supposed to be adjacent to B and E, done. But F is also supposed to be adjacent to G. So in that case, we'll go ahead and in the new drawing, we'll put G on the opposite side of the picture as F. And I'll go ahead and put in that edge as well. So that takes care of the top 4 vertices. Now we just have to finish off the bottom 4. How about we do C because we just did F. But C is adjacent to B, G, and D. So B we got, D we'll put in that edge, and G we'll put in that edge. Let's go ahead and finish up this left-hand side. So for H is supposed to be adjacent to, what is that, E, G, and D. So H, E, got it, D, and G. And notice as soon as we finish off H, it looks like we finished off D and G too, so let's do a quick double check. D is supposed to be adjacent to AHC, AHC, got it, and G is supposed to be adjacent to C, got it, H, got it, and F, got it. So notice we recopied the graph, and we were able to make it a bipartite graph or draw it in the normal 2-column way for a bipartite graph. Okay? Now, that is also a way to test to see if your graph is bipartite, to do that strategy. Now, that being said, the only way that these 2 graphs are isomorphic to each other is if that second graph that looked like a wheel is also a bipartite graph. So let's be smart about this one. We'll do exactly the same thing, but I'm going to do it up here next to the graph so we can make everything a little bigger so it's easier to see. And then before I post this, I'll go ahead and move that picture below so it's easy to read if you want to read this in a file. Okay. So again, you pick your favorite vertex. I'd probably pick 1 just because 1's the first number. And then you look and you say, all right, well, who is 1 adjacent to? Well, 1 is supposed to be adjacent to 2. 1 is also supposed to be adjacent to 8. And across the way, 1 is adjacent to 5 as well. So 2, 5, and 8. I'll make them numerical, or excuse me, ascending order for now. So then you have to use a vertex that you already have in play. Otherwise, you can get pieces and parts that don't actually line up or fit together well at the end. So then if we pick on vertex 2 is supposed to be adjacent to 3 other guys. So 1 we've already got. Then we have 3 and 6. So 2 is adjacent to both 3 and to 6. So we'll put 3 and 6 on the other side. And then we're done with 2. We have degree 3 in the newly drawn, trying to be bipartite graph, and they had degree 3 in the original one, so we're good so far. Then we pick another letter. which vertex would you guys like to pick next? 3, 5, 6, or 8? Hint, it doesn't matter which one. Yeah, sure, 3 works. Although I had a vote for both of them. All right, we'll do them both in that order. So if we start off here with 3, 3 is adjacent to 2, it's adjacent to 4, and it's adjacent to 7. 3 was what? Let me grab the other color. So 2, 4, and 7. So when we put this in, 2 we've already got, 4 and 7 we have to put down here. Okay. Now, if we then look at vertex 5, here's where fun things come in. Vertex 5 is adjacent to 6 and to 1. No worries there. But vertex 5 is also adjacent to vertex 4, which means you have that edge. Now, what's the issue with putting in that edge? Yep, you guys nailed it in 1, or in 2, since there's 2 answers so far. As soon as you get this edge right here, that is an edge inside of one of those vertex sets, one of those vertex sides in this case, the right side in this case, that tells you that it is not bipartite. Now, we actually could tell that it was not going to be isomorphic before we got to that edge that made it not bipartite. Anybody spot how I could tell that the 2 graphs weren't going to be isomorphic even before we got that edge? Anybody notice what happened with the vertices when we were building our supposedly, hopefully bipartite graph here? In other words, even if the second graph had been bipartite, they wouldn't be isomorphic. That is because of this issue. You got it. The number of vertices in the 2 columns are not the same. So even if you have 2 bipartite graphs, if the number of vertices in your 2 sets or in the 2 columns or the 2 sides or the 2 rows, however you've drawn it out, are different, they're not going to be isomorphic. So as soon as I was having to draw that 7 down here when we were looking at vertex 3, that would tell you right there that either you screwed up somewhere, or even if it's bipartite, you're not going to get isomorphism. It's not going to be isomorphic to each other. Okay? But if we put this all together, just the fact that we did not have 2 bipartite graphs, that's going to tell us right here that these 2 original graphs are not isomorphic to each other. So let's write that at the end of this problem, and then we'll look at the beginning part of section 1.3. So, conclusion. Because one of, apparently I cannot spell one of the graphs is bipartite and the other one isn't, we're going to get that our 2 graphs are not isomorphic. Okay. You can. The only reason why I wouldn't recommend putting your vertices in the 2 columns first is just because for most people it's extraordinarily difficult to divide your vertices up in the correct orientation. I mean, when we looked back at this original one that did turn out to be a bipartite graph, several of us, myself included, would have loved to go ahead and put A, B, C, D on one side and E, F, G, H on the other. Now, that obviously wasn't going to work if you thought about it at all, because A, B has an edge between it. So you're going to have some of the ones on the outside and some of the ones on the inside. And this is one of the reasons I color-coded it, so you could easily see which went into which piece. The blue ones went into one of the sets, and the yellow ones went into the other set. Some people can actually look at these and be like, hey, I think this collection of vertices go on one side and this collection of vertices go on the other side, but most people can't do it, and quite honestly, I think it's faster to, instead of trying to figure out which numbers to put on which side, to just go ahead and put an arbitrary one on one side and build it from the edges. Yeah, okay, I get what you're saying now. No, the order in which you look at the vertices, that part doesn't matter. At the end of the day, you will have a graph, whether it's bipartite or not isomorphic, to if somebody started with different vertices. So no, you could totally have, when we were doing this here, you totally could have, instead of like picking 2 here like we did second, you could have picked the 5. Or like what you just said, we did 3 and then 5, you could have done 5 first and then 3. If you'd done 5 first, you would have had these edges over here on this side. And that's perfectly fine. You still would have gotten the same issue of having an edge in one of the 2 columns. All right, so that is it for this section. Let us look at section 1.3. So section 1.3 actually deals with some stuff we've already talked about. The main thing that section 1.3 deals with is, well, it's called edge counting. So it's dealing with, well, edges. It's self-descriptive here, okay? So the question that just came in was, can 2 graphs be both bipartite and not isomorphic? And the answer is yes. Here, let me show a quick example of that. So, example here, bipartite, but not isomorphic. And I'm going to be relatively lazy with this example, so it's going to be a pretty small example. So suppose you have somebody like this. I really like it like that, I have to be honest. So suppose, oh, I don't know, about something like that, okay? So this is almost a complete bipartite graph on 3 and 2 vertices. So this is G. There's a couple different ways that you can have bipartite graphs that are not isomorphic. First one is, suppose you have this guy. Still bipartite, but notice it doesn't have the right number of vertices and edges, okay? Now, if you actually do have the same number of vertices, you can also have issues. But that's a really easy one to show there. I'm trying to think of another letter other than H, and it didn't happen. But you can also have things like, maybe you have the exact same number of vertices, but maybe your edges are a little bit different. So here, in this particular example, my example was almost too simple to give an awesome example. That one still has a different number of edges. Just because of the way I drew this first one here, I wasn't actually able to draw one that is not isomorphic and still had the same number of edges and vertices, just because of how I drew the first one. Okay. Almost. I only had one of them that was missing. Which edge is missing here? The edge from this top right all the way down to that bottom left. So yeah, when you're really close to your complete graph right there, it's hard to redraw it and not be isomorphic. You remember when we drew out all the guys isomorphic or not isomorphic to each other a little bit ago? When we got really close to the complete graph, there was only one guy that was what everybody was going to be isomorphic to. Similar right here. I did not, actually, although it is a tie-in. If you can actually, we haven't talked about colorings yet. We're going to deal with colorings in Chapter 2, so next week. But if you actually get where you color your vertices and you do a proper graph coloring in only 2 colors, that actually is one of the conditions for being bipartite. I colored them here just so you could see exactly where I was looking, because unlike if we were together and I could point with my fingers, look here, I can't do that because you can't see me pointing. Yeah, you can. You can put in an extra edge here, but it would still be isomorphic to this one. I was trying to draw one that was not isomorphic. All right, did that take care of most of the isomorphic questions? I realize it may not be everything, but at least the immediate ones right now. Where are you saying? Bottom left. This one and that one? Yeah, it would be isomorphic. If you flip it upside down, it would be the same as this one. The one you're talking about is that guy. And that would actually force it to be isomorphic. Yeah, that was my same issue because I was meaning to put in, if not that edge, one of a similar one, and I was like, oh no, it's not isomorphic. So yeah, you got to watch out for those things. And it's not always, sometimes you get halfway through and you're drawing it and you're just like, nope, didn't work how I planned it to. All right, so on to section 1.3, which deals with counting up your edges, or how many edges are in a graph. And the first property, which is quite honestly the main property in the section, there are 3 main properties in the section. This one right here is something we've already talked about. Now, note about your textbook. Your textbook restarts the numbering of all of his theorems in each section. So throughout our course, we will have many theorem 1s. Don't bother with the name, or don't bother trying to memorize the name unless you actually want to say something like theorem 1 from section 1.3. Having a cheat sheet somewhere that says, I need to find this in this location may just be sufficient. So as long as you're in a simple graph, this works. If you're in a directed graph or a multi-graph, a variant on this still works. Okay? So in any simple graph, if you add up the degrees of all the vertices in your graph, that's going to be equal to twice the number of edges. And in symbols, it's this thing right here, twice the number of edges, the 2 times the number of edges, the degree of each vertex, where V comes from the vertex set, and you add them all up. This is the same summation symbol that you would have had back in a Calc 2 class. Now, if you did remember Calc 2, they normally did indices where you had something like I equals 1 to n. This notation down here means we're not going to label them like that. This just means take every single vertex from your vertex set, take the degree, and then add all those degrees together. It's a little bit more advanced way of dealing with summations. Now, like I said, we've done that before, but if we look at a baby example just to remind ourselves of why this works, if we look at each one of these vertices, we'll have vertex A, B, C, and D. We'll deal with the corollary here in just a second. And the degree of each of these guys, to some extent, this is showing you how to deal with the formula too. The degree of vertex A, 1, B is 3, C is 2, and D is 2. I am assuming that you guys are all comfortable with that at this point. We have a grand total of 4 vertices, and just to make sure we're all on the same page, if we then sum up all of those degrees, so using that same symbol we just had there just a second ago, what would be that sum? Did anybody happen to add up all those degrees yet? Yep, it would turn out to be 8. And quick check, how many edges do we actually have in this graph? Yep, it is going to be 4. Now, obviously, if you multiply 4 times 2, you're going to get 8, so this formula works in this one example. It does turn out to work in all examples, and we talked about why previously. Anybody remember why it worked? Or anybody remember why that relationship has the 2 being correct? And that was because each edge has 2 ends, and when you count up the degrees, you're counting each end once, so that means you've counted each edge a total of 2 times. Okay? One of the ways to find the total number of edges is what we've done in the past, add up all the degrees and divide by that factor of 2. Okay? So that's something we've talked about before. We actually got a little ahead of ourselves when we talked about it before. But one of the things to note is while we did spend quite a long time in section 1.1, part of that is because we actually did talk about things that your author of your textbook didn't talk about until some later sections. So you're going to see some things that are feeling a little bit familiar as we go through the other sections. Now, a corollary, and I'm not sure if you guys know the details of the corollary or not, depends how much you've dealt with them in the past. Corollaries are direct results or immediate consequences of some theorem. So this corollary of the previous theorem says if you're in some graph, and I should totally add in, we are looking at simple graphs, okay? Then the total number of vertices that have an odd degree turns out there has to be an even number of those type of vertices. Okay? So, for example, up here, notice we had 2 vertices that had an even degree and 2 vertices with an odd degree. Turns out it doesn't matter how many vertices have an even degree, but it does matter how many vertices have an odd degree. You have to have an even number of vertices with an odd degree, which just seems absolutely weird and bizarre until you start thinking about it. Okay? So let us look at why this would be true. And let me go ahead and make this a slightly different color so you can see where the work starts, or where the explanation starts. So I'm just going to broad strokes the reason. Excuse me. So let's suppose we do the following. So suppose we have some graph that doesn't adhere to this criteria. So we have a graph where we have an odd number of vertices, and all of those vertices have odd degrees. And maybe this graph also has some vertices with even degree. We don't know how many of them there are, and honestly, we don't really care about them as much. Okay? Then, if we apply our theorem 1 from above, and I'll go ahead and abbreviate theorem because I'm lazy. If we sum up all the degrees of all of the vertices, both the vertices with odd degree and the vertices with even degree, notice what will happen. We can actually partition it out. We can say the sum of all the degrees where the degree of those vertices is even. Okay? Now, if your degree is even and you add up a bunch of different even numbers, maybe they're all the same even number, maybe it's a bunch of different even numbers, this sum is going to be what? An even number or an odd number? What do you guys think? You add up a bunch of even numbers, the final sum should be what? Even or odd? Yeah, it should actually be even. Now, that's only dealing with all of the vertices where the degree is even, so we also have to deal with all of our vertices where the degree is odd. So this is the sum of the degrees where the degree is odd, but I'm going to sum up all of them except for one of them. All but one. Okay. And then we'll put that one last one at the end. Degree of one vertex, and that guy has an odd degree. Okay. Well, what do we know? That last one definitely is going to be an odd number, because we said it was an odd number. Oh, I wrote that wrong. But over here, we said we had an odd number of vertices with odd degree, so if we pulled one of them out, that means there's an even number of vertices here. So this one here is going to be, if you have an even number of odd numbers and you add them all together, like 3 plus 5, add it together, 2 odds, the sum of 2 odds is even, the sum of 4 odds is still even, the sum of 6 odds is still even, so this is going to also give you an even number, which means we now have some sum that's an even number, some second sum that's an even number, plus an odd number at the end, and if you put that all together, are you going to get an even number or an odd number? What do you guys think? And yes, I see your last comment. That's the other way of showing it too. So here we're going to get an odd number, and this is a problem because that thing can never equal 2 times the number of edges, because we were supposed to be able to what? We were supposed to be able to get, well, 2 times the number of edges is always going to be an even number, and we got an odd number, so it's not possible. Now, what was our starting assumption? Our starting assumption was that we had an odd number of vertices with odd degree, and then we got to a place where we weren't allowed to get, so that means our assumption up here was wrong, which means we have to have an even number of vertices with odd degree. So this is saying why it couldn't ever not have the condition you're supposed to. The comment in the chat is a different way of saying it. Specifically here says if you're supposed to get an even answer, and the sum of all the even degrees is an even number, this over here is going to have to be an even number, which forces you, since you have all odd degrees that you're adding, forces you to have an even number of odd degreed vertices. which is just awkward to say out loud, okay? Did not mean to go over time a little bit there, so we're definitely going to stop there. Next time, what we'll do is we'll actually use this formula and go over a couple of examples to see where that formula of the sum of all the degrees of all the vertices is twice the number of edges, how and where that can be useful, but we'll do that next time.